Okay, time for another talk. We have some more heresy here, scientific heresy. Um, I have a paper here that just got put onto Vixra. The sun is a very young star. Now, I know a lot of the mainstreamers, they say, well, the sun is, 4.5 billion years old. It's about a little bit older than the Earth. But that's not necessarily true. Um, what happened is back in the day, the geologists and the astronomers, all the scientists all believed that the solar system was a single unit. All the objects in the solar system and the sun, all related, all came from the same nebulous material. So naturally, they should be the same age. And that was the assumption, a major assumption. So time goes on. Scientists are slowly figuring things out. The geologists, they started to realize that the Earth is vastly older than 6,000 years, as the young Earth creationists have it. It's many billions of years old. And then they started scratching their head because they were like, well, how can the Earth be, 3.5 plus 4.5 billion years old when we only have a method for powering the sun only lasting a max of 20 million years through slow gravitational contraction. Basically, what they had the sun as being powering the sun is that the whole body of the sun is just slowly collapsing on itself. And the very act of collapsing causes it to heat up. It's just like when you have those little demonstration tubes where you can take a little piece of cotton or something that's very flammable and you put it into a tube and you compress the tube really fast. The compression of the air causes the air to heat up really fast, and it can light that little piece of cotton inside the center of the tube up, and it can explode. It's the same principle behind diesel engines. The diesel engines don't necessarily have spark plugs. They have I think they're called some type of heater coil or something when they first start up. But eventually what happens is the actual motion of the engine is a feedback. So you have the fuel going in, and the force of the piston coming down into the chamber, pushing the diesel fuel down in the air mixture, it compresses it so violently that it heats up and then it explodes. It combusts on its own without the need for a spark plug, as does a gasoline engine. So think about the sun as a giant diesel chamber where the entire body of the sun is compressing itself. It's compressing itself so violently that it's heating the material up and it's causing it to be bright. So in short, they had the sun as being 20 million years old tops. Lord Kelvin had done those calculations. And then the geologists were in a huff and they were like, well, the Earth is billions of years old. Clearly, you can't have all the objects in the solar system all be the same age, because then it means the sun will have to have something that keeps her bright, hot, and shining for billions of years to make it match the age of the Earth. And that's the problem. They took an assumption and then they went off the deep end, like I said in an earlier talk. They went off the deep end. They took the assumption that all the objects in the solar system are all the same age. There was no evidence to show that to be true whatsoever. So naturally, when the geologists were saying the Earth, they found the Earth to be billions of years old through radiometric dating, they then said, well, look at the sun. Oh my gosh, that means the sun has to be billions of years old. That means we have to have something powering the sun besides gravitational collapse, because if we don't, then something's wrong. We got the age of the Earth wrong, or something's wrong. But they never looked at the assumption. They never looked at themselves and said, hey, listen, maybe the objects in the solar system aren't all the same age. That's what they should have questioned. But naturally, inside of scientific organizations, you're forbidden to question the root assumptions of the parent organization. As well, they didn't actually realize that it was a root assumption. Maybe they didn't realize it. They just went along with it, and everybody, went with the flow, and nobody questioned it, and everybody, saying kumbaya around a fire, and everybody got along with one another, and they could have careers and move up the career ladder and whatnot. But unfortunately, moving up the career ladder and getting to the truth are not the same thing. And that's why I wrote this paper, The Sun is a Very Young Star. Now, of course, I might be completely wrong about this, but what I did here is I measured the DH ratios of the Earth, and I compared them to Venus, Mars, Jupiter, Saturn, Neptune, Uranus, and the Sun. And now, I don't know if you guys understand particles or atoms or whatever, but apparently you have three isotopes of hydrogen. You have your hydrogen, you have your deuterium, and you have your tritium. Now, the difference between these two is not chemical. Chemical meaning it's that outer electron that determines if it's how it chemically reacts to stuff. It's that single electron that determines its chemical behavior. So the chemical behavior of hydrogen, deuterium, and tritium is all the same. The difference is their nuclear behavior. Hydrogen has one, now keep in mind, these are called hydrogen. But when you look at the isotopes, they're different. Hydrogen has one proton, deuterium has a proton and a neutron, and tritium has one proton and two neutrons. And this radioactively decays. The half-life on this is 12.32 years. And this is stable and this is stable. So this is the H and this is the D. So the DH ratio. The deuterium is twice as heavy as the hydrogen, but they're both the same. They're both the same elements. They're just different isotopes of the same element. So I took the two stable isotopes of the same element, mind you, the most abundant element in the entire universe, and the most abundant element in hot young stars, and I used those to determine how old an object is based off of the ratio between the heavier and the lighter hydrogen. And the rule of thumb here is the older the star is, the more deuterium there is versus the lighter isotope hydrogen. And the rationale behind that is evaporation back into interstellar space. To state it easier, let's just say you have balloons and you fill the balloons up with pure deuterium and you fill some balloons up with pure hydrogen. Now, deuterium is twice as heavy as the hydrogen. So when you release the balloons, which balloons are going to leave before or quicker, faster? They'll rise up quicker, and there's going to be more of them to leave. The lighter hydrogen is. The deuterium, the twice as heavy deuterium, it's going to be sluggish. They're going to take their time going up, which means as the star ages, it loses more and more and more of that lighter isotope of hydrogen, and the deuterium stays behind and combines with the oxygen, forming heavy water, what's called deuterated water. And over many billions of years, that ratio increases because there's more and more and more lighter hydrogen that escapes the atmosphere. Now, the reason why we can use this method is because most stars, when they're very young and hot, they're mostly composed of hydrogen gas, diatomic hydrogen gas and ionic hydrogen gas, or hydrogen ions, not hydrogen, you get what I'm saying. But basically, they're mostly hydrogen and helium. So to determine the ages of them, we can look at those ratios to determine how long it's been since that star has formed. And that being said, I'll get to the meat of this paper here in a second. Scientists took the Earth. Now, I know people might be still new to this. The Earth is a very highly evolved, very, very, very ancient star. It's the remains of the core of an ancient, really old star. So to find the hydrogen in the atmosphere, you're not exactly going to find it in the gas because it already would have escaped. The only hydrogen we're going to be able to find is if it gets locked up in crystalline structure inside of rocks and minerals, or if it's combined with the oxygen forming the water. And that's where we then get what's called the VSMOW, or the Vienna Standard Mean Ocean Water DH ratio. And that is 1 deuterium for every 6,420 hydrogens. So imagine you have 3 large high schools. Each high school has 2,000 kids. And then you have one teacher or principal to teach those 3 high schools. Now think about how many more hydrogen there are versus the deuterium. That's the ratio we're talking about here. 1 out of 6,420. That is what I have set here is about 4.5 billion years. You'll see that in the paper. And what you can do is if you multiply that ratio by 10, making it 1 out of 642 hydrogen, so 1 deuterium for every 642 hydrogen, you're sitting at an even older object, because remember, the deuterium ratio increases. So there's going to be a lot less hydrogen there, which means the star can be dated as being 45 billion years old. If you go in reverse, and you have 1 deuterium for every 64,200 hydrogen, you're looking at the star as being 450 million years old. And so on and so forth. And I wrote that in the paper. You guys can read this. So basically, that leaves us a method for calculating the age of objects that have significant deuterium to hydrogen ratios available either in the atmosphere or locked up in crystalline structure in the rocks and minerals in the ground. So it's kind of like taking an ice core sample, and I wrote that in here. When it snows in Antarctica, the snow compacts over many hundreds of thousands of years, and determining what the ancient atmosphere was can be determined by looking at when that snow had got compacted, and then it pushes down and pushes down and pushes down. And what they do is they drill out a big cylinder very deep into the snowpack, into the ice, and they pull out these samples, and they can look at the ancient atmosphere based off of how deep the ice goes. With the DH ratios, what we can also do is determine when that material or what kind of atmospheric conditions that material formed in based off of the deuterium and hydrogen ratio made available. Because remember, these scientists, these people that take these measurements, they don't actually connect them to being able to determine how old an object is using this ratio, because they don't have an initial value. They don't have a 0 point. They don't have stars being the young, hot planets. To them, it's just a random ratio that they can measure and finagle around with numbers and do weird things and make pretty graphs and stuff. They don't actually make the connection with its ability to be able to determine how old something is. And that's why I had to write this paper. But unfortunately, it's this is where the heresy part kicks in. The Genesis mission, the mission that they sent, I think back in 2004, to take solar wind samples. So basically it had these little plates, these little silicon plates, and the Genesis spacecraft would go up and it would let the solar wind hit these little plates and collect all the solar wind material coming out of the sun. And then they would take the Genesis mission back. Unfortunately, it crashed, and they took some material out of those silicon wafers, and they took them to the lab and cleaned up all the dust off of them and took the samples that they needed and made measurements. What they had found is that the solar wind, the DH ratio, which wasn't their main goal. The DH ratio wasn't their main goal. The main goal was the oxygen and nitrogen ratios. But the DH ratios that they had measured were 10 times lower than what they had expected to find. In terms of this theory, 10 times a lower DH ratio essentially means 10 times younger. So what I have here is the measurement. So in one of the silicon wafers, it says SiB/C. The corrugated data and the SRIN profile, which they look at the graph and they look at all the measurements and they make averages out, was 2.3 times 10 to the negative 7. And 2.3 times 10 to the negative 7, 2.0 times 10 to the negative 7, and then 4.5 times 10 to the negative 7. Using the calculations I have outlined in this paper, those three ages make the sun between 5.8 million and 13.13 million years old. What this means, ladies and gentlemen, is that the sun is not 4.5 billion years old. It's not the same age as the Earth. It's a very, very young star. And that goes into the face, that flies in the face of the accepted wisdom or the accepted paradigm of the establishment. But it does not fly in the face of the theory I've been developing. For those who haven't seen this graph, I've showed this graph a lot more times. The young hot stars fit up here. Now, I don't have the ages exactly spot on, but these can always be adjusted in the future. The main goal is to have it go off logarithmically, meaning it starts small, and then it gets a little bit larger, a little bit larger, a little bit larger. And by the time you get over here, the age differences are a lot bigger, like 1 trillion years to 10 trillion years. And so basically the sun is like up here somewhere. And 5.8 to 13.13 million years old, that is definitely very, very new. I haven't seen anybody write anything like that down. Even Kelvin's calculations of the sun slowly gravitationally contracting, he had it as around 20 million years old. But to think if this method is actually much more accurate to determine the ages of the stars versus, the age of the Earth. So basically what this means is the DH ratio is dependent upon the accuracy of our measurements. And if this method turns out to be as useful as I think it's going to be. As well as this method, I have this method as dating Venus, the apparent Earth twin, as being between 450 billion and 700 billion years old. It's a very, very, very old dead object. There's no life on it. There's no volcanoes. That thing's dead. And Mercury, I have Mercury. I think I used gyrochronology to measure the age of that. That's 7 trillion to 32.75 trillion years old. I have Neptune and Uranus as 1.1 and 1.2 billion years old. And I have Saturn as 590 million, and I have Jupiter as around 700 million years old. So what this means is that between 5.8 to 13 million years old to a 590 million year old object such as Saturn, we have a way to determine how old the stars are now. And if we can just get those DH ratios off the younger stars, such as the red dwarfs and the orange dwarfs and all that, we can actually determine how old they are now. But of course, the accuracy of the measurements is going to be needed. All right, guys, I made this video way long enough. Hi, Celeste. Bye.